Next speaker is Suhail Sherif talking about parity decision trees and listening. It really has something to do with resolution.
Yeah, so if you look outside, it says this talk is by Arkadev Chattopadhyay, but it's actually by me, Suhail. And outside, it also says that there are applications to proof complexity, and that is true. And so don't worry, that is also the direction with which I will be approaching this talk. So to start with, the talk is titled Lifting to Parity Decision Trees via Stifling. So it's really a result about parity decision trees. It's the avenue through which I myself approached proof complexity. So this is going to be pretty much along the lines of my thought process. This is joint work with Arkadev, Nikhil, and Swagato. And we'll start with why proof complexity leads us to think about parity decision trees. So this has all been said before, but we're just going to do a quick run through. In proof complexity, you have, in general, an unsatisfiable CNF, and you want to prove that there is no satisfying assignment. And we know that such proofs should be quite large if we assume that NP is not equal to QNP, at least for some CNFs. And what we want to do is we want to prove that for certain definitions of proofs, that we can actually show this, that there are CNFs for which proofs under this definition have to be large. And the definitions that we'll be interested in are quite computational. And to lead to this, let's rephrase an unsatisfiable CNF as the condition that every assignment to the variables falsifies a clause. Right? And this naturally leads us to this relation, the false clause relation. And it relates assignments in 0, 1 to the n to clauses in your CNF. And the relation is just x is related to I if the assignment x falsifies clause I. And in this language, what we want to prove is that this relation, the false clause relation, is total. That is, for every single assignment, there is some clause that it is related to. And this is a relation, and obviously in theoretical computer science, we're very much interested in the complexity of computing relations. And we'll see that in the case of decision trees, a decision tree that actually computes this relation is indeed a proof that our CNF is unsatisfiable. So as an example here, we'll take this simple CNF, which has 3 clauses. A decision tree is a way to map assignments to clauses in this context. And what it does is it specifies a variable, x1. So you query what x1 is. If it's 0, you take this path. If it's 1, you take this path, and you recurse until you reach a leaf. And you output whatever value there is at the leaf. So it's clear from this that every input is being related to some clause number. So if you give me a decision tree, that part of it, the totality of the decision tree is evident. All that we need to verify is that the decision tree is actually computing the relation in question. So what we need to verify is that for every single leaf L, the inputs that reach that specific leaf L do actually falsify the clause that you're outputting over there. So for example, if you take the second leaf here, every input that reaches this leaf has x1 set to 1 and x2 set to 0. And that is, in fact, sufficient to falsify the second clause over here. So this is just a quick run through of how a decision tree of size S is indeed a proof of size S. Now, they're not just proofs, they're actually well-studied proofs. They are exactly tree-like resolution proofs. So this is what a tree-like resolution proof would look like. You take clauses from your CNF, and then you do the resolution action. There's an x2 and a not x2 here, so you can resolve that out. Then x1 and not x1, you resolve when you get the empty clause. And this proof is exactly the same as this decision tree. It's just flipped upside down. These are the clauses 1, 2, and 3. This is your internal node, and this is your root node. And this is true in general. It's a quite simple relationship. And since this is well studied, it must be the case that we know CNFs for which this proof system requires large proofs. And indeed, that's true. So the pigeonhole principle and the cite-in principle are 2 important CNFs that we'll be talking about in this talk. So in the pigeonhole principle, you have a variable for every pigeon and every hole. And that variable tells you whether that pigeon P is in that hole H. And what the pigeonhole principle states, it states that every pigeon is in a hole. That's basically saying that the OR of these variables in a row is 1. That's a single clause. And the other constraints that you have is every hole has greater than 1 pigeon. Wait, sorry, no hole has greater than 1 pigeon. There's something wrong there. So for that, that's also quite simply, it's a polynomial number of clauses. Both of these constraints together cannot be satisfied. So this is an unsat CNF. And the question is, are there proofs that every assignment does falsify a clause in a decision tree proof? And the answer to that is no. Any decision tree that actually proves this really needs a very large size. And the other one we're interested in is the Stifling CNF. So you have a constant degree graph G with an odd number of vertices, the way I prefer to state it. And there's a variable for every single edge, which is telling you whether to include that edge or whether to drop that edge. So for every single assignment to your variables, you have a different graph Gx. And you have constraints that are stating that every vertex has odd degree. So the constraint that, say, vertex 1 has odd degree is a constraint really only on these 3 edges here, on a constant number of edges. And so it can be written as a CNF of constant size. And so if you take all these vertices together, that's a CNF of order n clauses. And it's proven to be hard whenever G is an expander. This requires large decision tree size in order to prove this. So when I say decision tree size in order to prove this, that also is what I mean is you require a large decision tree in order to solve the false clause search problem. All right, so this is a quick introduction to things that we've already seen. So now I'm going to move on to slightly stronger proof systems. So one of these is quite common, which are decision DAGs or just basic resolution proofs. Whatever proofs you get just by doing only the resolution rule. So these, if you think of them as decision trees, you have to make some modifications. You have to make them into a DAG format. And from the perspective of a decision tree in which you're querying variables, the only modification you have to make is that you can forget some of your variables. So although you could have had 2 different computational paths, which are remembering different things, they can forget variables and reach the same state, which is how it's actually compressing your decision tree. So even though you're remembering different things here and different things here, after some queries, if you forget some stuff, it's possible that you're remembering the exact same state at some other point. And what this allows you to do by using this DAG structure is, in this, if you think of it in terms of resolution proofs, it's allowing you to reuse the line that you've already derived in multiple derivations. Right, all of this is really just background, but I should mention here that decision DAGs do actually give you a huge saving. You can go from exponential size proofs to poly-size proofs by changing from decision trees to decision DAGs for some CNFs. It's not the case for the pigeonhole principle, and it's also not the case for the Stifling principle. But we're not going to be actually looking too much at this strengthening of the proof system. The strengthening that we're interested in, and what finally brings parity decision trees into the talk, is if you're trying to compute this relation via parity decision tree. Okay, so this is really the starting point of the talk. If there are any questions till now before this. Okay, so from here on, I think I can take it a bit slower. Right, so the difference between a decision tree and a parity decision tree is that instead of querying bits, you're actually querying entire parities. So instead of just being an index of from 1 to n here, it's actually a subset of 1 to n. And the answer that you get is the parity of that subset of bits. And again, the statements are still as before. This decision tree defines a total relation from inputs to clauses, and it's easy to verify that it does actually compute the false clause search problem. So I will skip over those. Now, it turns out that parity decision trees are exactly tree-like res plus proofs. So in this res plus proof, every line, instead of just being a clause which is a disjunction of literals, now every line is a disjunction of parities. So it's x1 plus x2 is equal to 0, or x1 plus x3 plus x5 is 1. This is the general format that you would see of a line. And you're allowed to do the resolution rule, again, very similar to the normal resolution rule, where if you have a parity set in 2 different ways in 2 different lines, you can get rid of that parity and just keep the rest of the clauses. So that's the resolution rule. One problem is that it's not immediately clear whether you can do resolution on two lines, because lines can be written equivalently. So for instance, these two here, this has x1 plus x3 plus x5 is 1. This has x2 plus x3 plus x5 is 0, but it turns out that these two lines are equivalent. So in a parity decision tree, when you think of it as a tree like res plus proof, we're actually allowing it a semantic derivation. So even though it might not be of the form p equal to 0 and p equal to 1 when you look at two lines, we're assuming that it can implicitly figure out whether it can be made into this form so that you can do resolution. If you want to explicitly make it into this form, you can do a rebasing rule, which is to change the basis with which you're looking at these parities. In that case, if you have P1 or P2, you can replace it with P1 or not P1 plus P2, which is exactly what I've done here. So not of x1 plus x2 is 0 is x1 plus x2 is 1. If you add that to x1 plus x3 plus x5 is 1, you get exactly x2 plus x3 plus x5 is 0. So the rebasing rule, it doesn't really change anything, because if you do the rebasing rule to this conclusion, you get this back. So these two are exactly equivalent. And you can also define parity DAGs instead of parity decision trees. And what we know is, so it has been proven that the pigeonhole principle is hard even if you use parity decision trees in the stronger variant. The Cyton graph becomes easy because it's all about parities. It turns out to be very easily solvable for PDTs. But yeah, it's clear that we do have lower bounds against parity decision trees. The place where we have no lower bounds is parity DAGs. This is just the res plus system. We don't know of CNFs that are hard for parity DAGs. So this is the goal we would like to strive towards. But towards this goal, what we want to first figure out is, why is it harder to prove lower bounds against parity decision trees or parity DAGs? So one reason is that a parity,
Just for Cyton, I guess you just ask the parities like in sequence and
yeah, so you can kind of
can you do something low depth, I guess was my question. Like
you can do low depth. You can do a binary search, and you can ask like the parity of like this half of the graph. One of them will be odd, one of them will be even, and you can kind of zone in on where you want to see. Right, so why are parity lower bounds harder? And this is not just a question in proof complexity. This is a question I was originally interested in, and which led to this paper, which then had applications in proof complexity, and so I'm here. So this is really why I'm here. So one thing is parity constraints. There are correlations between multiple bits. Right? You're saying that all these bits together, there are an even number of ones in them. So it's really not easy to think about. Generally, you can think of querying a bit and finding out the value of that bit. And then you have an idea of what you know and what you don't know. When you have parity constraints, it becomes just much harder to think about, which is something we would like to do. Another reason is that there are really a lot of parity queries that can be made. Instead of just being n queries that you can make, there are now this vast number of queries you can make. And in fact, there's a famous size width trade-off that you have for decision decision DAGs, or just for resolution proofs, you have a size width trade-off. And that proof doesn't work with parity queries exactly because there are so many different parity queries that could have been made. So for parity DAGs, we don't even have this statement that if you have large width, it implies large size. This probably should not have been trade-off. It's just relation between size and width, not a trade-off. So this raises a question. Parities, all these parities are strong. What tricks can we use in order to tame the power of these parities? What tricks can we use to make them easier to work with? Or if you will, what are some parity poopers? And that's what this talk is going to be about. We're just going to look at a variety of different ways in which we can somewhat tame the power of parity queries. So we're going to start with this paper here of Itsikson and Sokolov. They prove various lower bounds for parity decision trees. So they show that the pigeonhole principle is hard. They show for a CNF related to Satan that is actually hard for parity decision trees. And they have other interesting results. Generally, you would give previous results, then you would compare it to your results and show how your results are better. Both of these authors are in the audience, and I do not fancy my chances in a 2-on-1 fight. So actually, all their works are completely incomparable to ours, and they're all very interesting. And I think that it's really good that we're getting these various ways to attack parity lower bounds. And I think we need more such ways. That's really the goal of my talk. It's a call to action. Find more ways in which we can control parity lower bounds. So let's start with their lower bound for the pigeonhole principle. So what is the weakness of parity queries that they exploit? Well, that's basically this. If you have k parity constraints that are set, that is, you have k linear equations in F2. And if you have a solution here, which I'm just writing as A1 to AN, then for any k plus 1 indices in these 10 indices, you can find a different solution which also satisfies the exact same k parity constraints, but differs only in those indices. So to be clear, suppose k was just 3. And so let's take this set S, which is of size 4. It says that if you have one solution like this, I'll be able to find a different solution in which the values outside of S are exactly the same. It's still A1, A2, A3, A8, A9, and A10. But it changes inside S. And the proof of this is also quite simple. So what you do is you add extra parity constraints. I was hoping to write on this, but my computer doesn't work, so I have to look over here, which is a bit weird. So just bear with me for a bit. So let's just add, so let's add extra constraints for each bit outside of S. And there are at most n minus k minus 1 bits outside of S. Let's add many constraints. So those are fixing the bits outside of S. And now the total number of constraints that you have has gone up to at most n minus 1. So now you have n minus 1 constraints in an n-dimensional space. So if there's one solution, then there has to be more than one solution. So there has to be another solution which has the same bits set outside, but different values inside. And this fact is used to say that in the pigeonhole principle, if you want to output the false clause being pigeon P is in some hole, it's very hard to do that. So what I mean by this is, if you look at, suppose you're outputting that okay, pigeon 1 is in a hole was one of your clauses, and that clause is false. Well, that means that if you look at the first row of this thing, you have the pigeon and all those holes up there. What you're basically saying is that all of these values are 0. Right? But if you haven't made enough parity queries yet, you haven't set enough constraints, that means that if you take a large enough subset here, there should be a different solution to this in which the values here are different, which means that that pigeon is actually in some hole. And so you could not have actually said that that is the false clause. So this is a very rough look at that lower bound, but it's the essence of the lower bound. So this is their lower bound for the pigeonhole principle. They also had a different lower bound for a CNF related to Satan. So in Satan, we had one variable for every edge. So in this new CNF that we're going to create, which I'm calling F here, we have 2 variables for every edge. And using these variables, you're going to implicitly define an XE here. So you take these 2 variables, you take their AND, whatever that value is, you think of that as XE, and then you try to think of the Satan principle on the implicit XEs. Now the statement that vertex V has odd degree, initially it depended on a constant number of variables XE. Now it's going to depend on just twice as many variables in the Y world. And yeah, so basically, since it depends on only twice the degree of V variables, that means you can write it as a CNF with only that many clauses. So it's still, F is still a CNF with around the same number of clauses and still constant width. Right, so what is the weakness of parity queries that's exploited here? Well, here what they use is that if you have a small size parity decision tree that computes any relation, then you actually have a small or a low cost communication protocol that computes the same relation. So the idea of that is, let's take any parity decision tree, and let's look at an internal node of it. So this is some internal node V. You take the subtree rooted at V, and you take the part of the tree that's outside of it. So you're splitting the tree into two sets. And apparently it's very easy to check if your input would actually go to this vertex or not, if you're allowed communication complexity, if you're allowed a communication protocol. So with constant communication, you can find out whether your input would have gone outside of this subtree or whether it would pass through the subtree. And then you can just keep on cutting down the size of the tree in half each time, or by constant fraction each time. And so you get that the randomized communication complexity of the same problem solved by the PDT is at most log of the PDT size. And then they use another work which shows that in this CNFF, you can actually embed the disjointness function, embed in some sense. And so since we know that the randomized communication complexity of disjointness is large, that automatically implies that the PDT size of this should be exponential in n to the 1/3. So in their previous work, they used this in the previous result that we spoke about. They were using. So this was the weakness of parity queries that they exploited then, which is this nice combinatorial thing. In this result, what they're using is the fact that if the randomized communication complexity is large, then the PDT size should be large. This one, it's still important whenever you get a randomized communication complexity lower bound, it potentially gives you something. But I feel that this one is a bit of overkill. We should not need randomized communication complexity lower bounds in order to prove PDT size lower bounds. There should be an easier way to go about it. Like, I don't personally know an easier way to go about it for this CNF, but there are other CNFs for which we show that there are easier ways to go about them. And that brings us to our contributions. So what we do is we introduce a notion of stifling, which helps negate the power of parity queries. That should be negate the power of parity queries. It's easy to negate parity queries. And we use this notion of stifling in order to prove a simulation theorem with constant size gadgets. And this is something we're quite happy about. It's nice to have simulation theorems which use constant size gadgets. I'll get to what a simulation theorem is in a bit. And so with these together, we show that for every single decision tree lower bound, which is just a lower bound on tree-like resolution, we're going to get a related tree-like res plus lower bound, or a parity decision tree lower bound. And so that's a pretty large class, because we know how to prove decision tree lower bounds for many search problems. So there's a pretty large class of problems for which we're showing PDT lower bounds. Right. So from this point onwards, I'll start talking about our contributions, but this is a pretty long talk, so I think I should have many breaks in between. Are there any questions?
Yeah, can you say what stifling literally means?
What stifling literally means? Sure. So we'll get to that in a few slides.
No, like the word in the usual English.
English, so stifling, the dictionary definition, I'm not too sure. Suppressing, yeah, I guess that would be a.
Yeah. So generally suppressing speech is the normal.
Sure, suppressing their power, their agency, or.
Yeah, often with speech.
Oh, with speech specifically.
It's often with speech specifically. There was so if you ever saw All in the Family years and years ago, this is what Archie Bunker used to say to Edith all the time when he didn't want her to say something. Stifle.
Cool. You should have let me know that before the talk. All right.
So that Satan lower bound that you talked about, that was like basically Satan with and lifting.
That was Satan with and.
Okay. Just out of curiosity, like if I want Satan with or lifting, I would get the same thing, or is it very important that I do and?
Shouldn't matter at all. You're just changing the signs of the variable. It's just all
right.
I don't know if it has any implications for the CNF side of it? Yeah, it's just a two. Yeah. Should not.
Mentioned that for Python, there's like a small depth representation.
Yeah.
So, people expect that to be smaller depth representation. Like I think the way you said it was log depth,
Yeah, so I think you get a log.
and then there's one expect like log and.
Well, there are like omega n clauses, and each one is important. So
It's fan in two.
Oh,
yes.
okay. I see.
How much does parity as being mod 2 matter versus mod 3?
So mod 2 is really nice because we're always dealing with Boolean assignments.
Yeah.
Other mods are very hard for us to deal with. That's going to be one of the open problems.
Oh,
So first, we'll see why parity queries, although I described them as these global correlations, there's a view in which they don't actually seem that global. So consider all your n-bit string inputs. That's you're just given an hidden n-bit string, no constraints on it. And then suppose you query x1 plus x2 plus x3, and you find out that the answer is 1. Now, this seems like it's a global correlation. It's relating these three variables, x1, x2, and x3. But if you just rewrite this to just write it as x1 is equal to x2 plus x3 plus x1, x2 plus x3 plus 1, this, you can think of this as just being a constraint on x1. It's really not restricting x2 or x3. It's really weird that it should change like this because it's just an equivalent statement. But this is actually true. If you just think of x2 and x3 being unconstrained and just x1 having a constraint on it, you're getting exactly the set of assignments which satisfy this parity constraint. So the set of solutions to this one parity constraints is actually 0, 1 to the n minus 1 on everything except x1, and with x1 set appropriately based on whatever the value is in 0, 1 to the n minus 1. And whenever you get a new constraint now, those new constraints are only on n minus 1 bits. So what I mean by that is, suppose after that, someone told you that x1 plus x3 plus x5 is 0. This seems like it's a constraint that is also affecting x1. But since we know that x1 is equal to x2 plus x3 plus x plus 1, we can replace x1 with that. And this is, given that we have that constraint, we can rewrite this constraint to completely avoid x1. So what we've done here is we've taken any parity constraint, we've written it as a constraint on one variable, leaving everything else free, and have the fact that all new constraints are over only the free bits. So it's really nice. It's like you've set one bit and you have an n minus 1 dimensional space to play with. And this simple fact is going to lead us to very simple lower bounds for parity. So let's take this example here. So we have the majority function on 7 bits. We want to find out whether majority of them are 1 or majority of them are 0. And we're going to prove a parity query lower bound for this function. Suppose that somebody makes three parity queries. What we're going to do is we're going to answer them arbitrarily. We don't care what answer we give to those 3 parity queries, because even after answering those 3 parity queries, given our view of things, we've just affected 3 of the bits and 4 of the bits are still free. So that means that by setting those 4 bits to 0, the answer can be 0. By setting those 4 bits to 1, the answer can be 1. So really, after querying these 3 parities, you still don't know whether the output of majority is 0 or 1. And what I really like about this lower bound is that it completely ignores the fact that they're parity queries pretty much. And this is the basis for the stifling functions that we're going to define. A k-stifled function is a function that can ignore any k variables. So majority was very good for us because it could ignore any 3 variables and still set its value by looking at the other 4 variables. In general, we say a function is k-stifled if for every subset of size k or less, there exist partial assignments to the other variables, which actually fix the value of the function, right? So there's an assignment x0 to the variables outside of this, such that if you take any completion of this partial assignment, the output of the function is 0. And there is similarly a partial assignment x1, such that if you take any completion on the bits outside of this, the function value is 1. And this is also why we call it we probably should be called a stifling function. So what's happening here is stifling. We're saying for any set of s bits, if the other bits collude, they can completely stifle the influence of these s bits, and they can ensure that the function is set to whatever value they want to set it to. So what we saw earlier was, or what's easy to see, is that majority on 2n plus 1 bits is n stifled. Like any n bits, I can ignore them and still set the function value to whatever I want. And that, so for any k stifled function, the PDT complexity of that function is at least k. So let's take another example of what a stifling function can be. So the indexing function, which is very commonly used for composition. So it takes 2 inputs really. Or you can think of its input as being in 2 parts. One is an n-bit string, and the other one is a 2 to the n-bit string. And we think of the n-bit string as being an index into the 2 to the n-bit string. It's pointing to one of the 2 to the n bits. And the output of indexing is basically what is the value of that bit that is pointed to. So you can think of it like this, and we're going to show that any n bits that you give me are actually going to be stifled by the rest of the bits of indexing. So suppose that these are the stifled bits, that's a bits from x and n minus a bits from y. We want to stifle them. Well, there are really n minus a bits that we have no control over. We have control over all the other bits. So what we want to ensure really is that whatever x we're putting in here does not point to any of these n minus a bits. If we can ensure that, then we can stifle it. And there are 2 to the n minus a ways to set the free bits in x. Since there were at most n minus a ways to set the bits in x to point to one of these stifled bits here, the fact that there are 2 to the n minus a ways to fix the free bits means that for most of the ways you fix the free bits, it's impossible to point to a stifled bit. Only n minus a ways of, at most n minus a ways of these could have possibly pointed to a stifled bit. So yeah. So we fix any of the settings of the free bits in x, which don't point to a stifled bit. And then you set all the other bits in y to 0 or 1, depending on whether you want the function to output 0 or 1. So the indexing function is n stifled. So what we prove using this stifled function definition is that for any relation R, the PDT complexity of R composed with F, again, I should probably get to what that means. Actually, it'll come on the next slide. So the PDT function of a relation related to R, which uses the function F, is at least k times the decision tree complexity of the original relation. The PDT size of the relation composed with F is at least 2 to the power k times the decision tree complexity of R. And we also have similar results for other measures, which are also interesting, but they might also be interesting in proof complexity, but we haven't seen them used yet, which is the subspace decision tree complexity, where you can query whether your input is in a subspace instead of just querying a parity, and the non-adaptive variance of these measures. So let's take our relation R to be the false clause search on the Satan problem, and let F be any function that is k stifled, which we're assuming its arity is t here. So again, we know the variables that are involved in Satan, which is a variable for each edge. In our R composed with F, we're replacing each variable in R with t variables. And the idea, similar to what we had earlier, is that we're implicitly defining what xe is using these t variables and using the function that we're composing with. So the XE variable is implicitly f of the YE variables. Again, because all the clauses over here were just on a constant number of variables XE, we can again make exactly the same argument here and say that the number of clauses that are going to be used, that are going to be needed to represent R composed with F is going to be at most 2 to the power T times how many ever clauses were used by R. That was very, that wasn't very mathy, but I hope it's clear. And again, the width of the clauses is small. So if we can, if T is a constant, this is all very nice for us. And T is actually going to be a constant whenever we use it. And one important fact that we want here is if you find a falsified clause in this R composed with F, it actually gives you a falsified clause in R. So to see that, we can think of, let's just look at what R is. R has a bunch of clauses, so C1 and C2 and C3. Now for each of the clauses here, we had a bunch of clauses that came out of it. Let's say D11, D12, and so on. Each of these gave rise to a bunch of clauses. And that's how we built our CNF for R composed with F. And if you run if you compute false clause search over R composed with F, it'll tell you, hey, one of your clauses here was false. And if this clause here is false, it actually implies that in your implicit X, that this clause is false. Because this is a CNF and this is an AND of constraints. So if you find a falsified clause for your R composed with F, it actually does give you a falsified clause for X. So this brings us to how are we actually going to prove lower bounds in general? Like before we figure out how we prove parity decision tree lower bounds, let's just talk a bit about lower bounds in query complexity in general. But before that, I guess I'll stop for questions again. Sorry? By composition? Sure. So composition here is exactly this. So you have some computational task you're working on here. Here, for instance, you have R. And R takes as input n variables or m variables. There's one variable for each edge over here. So you can think of that as x1, x2 to xm. And by composition, I'm going to define a new relation which doesn't directly work with these inputs. So you can think of, let me just erase some of this. So earlier what we had was all of these were being used to compute. Now what I'm going to do is I'm going to replace each of these with an instance of F. And F itself takes T variables as input. So there's y11 to y1t, ym1, yn. So we're dealing with this is what we call a composed relation, where its inputs are these y variables, and to output an answer, we can find out what the valid outputs of this are by actually computing F on these y variables, getting a bit here, and doing them for each of this, and then using that as an input for second. That's what a composed relation is. And what this last line is saying on this slide, it's saying that if you solve the false clause search problem for the CNF R composed with F, it's actually computing this composed relation of Satan composed with F. So how do you prove lower bounds in general? So very similar to the prover delayer game, you can think of the querier adversary game. And it's probably exactly the same game. So the querier makes queries to your inputs, the adversary answers them. What the querier wants to do is it wants to output some value. It wants to output an I. such that for every single input that's consistent with all the queries and their answers till now, I should actually be a valid output. And if the adversary can force the querier to make k queries before answering, that means that the decision tree complexity of the task was at least k. And in fact, it's an if and only if. As in, if k is the maximum number of queries that the adversary can force, then the decision tree complexity is exactly equal to k. So the question now is, if we want to prove a lower bound, what kind of adversary do we need? How can we force the querier to make many queries? So how are we going to be an adversary for this computational task R composed with F? So let's just take 4 bits here. So there are these implicit bits xe1 to xe4 for each of the edges. And there are these t-bit blocks that correspond to each of these xe's. And whenever a new parity query is made, what we're going to do is we're going to do exactly what we did for the majority function. A new parity query is made, we answer it arbitrarily, and we think of it as just affecting one of the bits, and the rest of the bits are completely free. So say maybe it affected that bit over there. And every time a new parity query is made, it might affect one more bit somewhere else. So when I say a new parity query, I mean a parity query that's independent of all previous parity queries. If your parity query depends on your previous parity queries, you already know what to answer. So these are generally new parity queries. Whenever a block has k bits affected, where f is a k-stifled function, so if suppose this block gets 2 affected, what we're going to do is we're going to query xei. So here, that's the second block. So what I mean here by query xei, we're an adversary, we shouldn't be querying anything. So what we're going to do is we're going to simulate a querier adversary game for R mentally. So we're going to think of an adversary for R, and we're going to ask it, can you tell me what the value of the second bit is? And it's going to give us some answer. Whatever that answer is, because our function is k-stifled, it means that we can fill in the rest of the bits here in order to ensure that whatever answer was given to us is actually consistent with whatever bits we have here. So once we've done the step of querying xe2 and setting the remaining bits in order to ensure that the output is exactly what the answer was, we've ensured that everything is kosher. Yeah. And now these new bits, the new bits that we set, we also think of them as constraints. So now when I say a new parity query is made, this new parity query is not just with respect to the old parity queries, but also with respect to the extra bits that we set. It should be independent of all of those. Right, so it's a very simple strategy for us. We're just answering queries arbitrarily. And whenever some block gets 2 affected, we're just setting the rest of the bits in it. And we're going to show that this adversary actually gives us all the results that we wanted. So suppose the querier made k times the decision tree of R parity queries. That means that the number of blocks where k parities were marked has to be less than dt of R. What that means is that in our internal simulation, we have made less than dt of R queries to the adversary for R. And because of the very definition of the R adversary, this means that we don't know what the output of the function is. In our internal game where we're querying the xe's, we don't know what the output should be. And since each unqueried xei, so suppose I've made these queries and these are all set, so this is set to 0. In each of the unqueried xe's, we can still independently set them to whatever we want. Again, because of the k-stifled nature, we can just set the free bits to set them to whatever we want. And so we can actually get any realization of the x's on the free bits. So that means that even the person who's doing the parity queries still doesn't know what the output of R should be. So we cannot answer R, and therefore we cannot answer the answer of R composed with F. So yeah, it should really be that we as the adversary cannot answer R, and therefore the querier cannot answer R composed with F.
for the composed function, constructed decision tree for the original function?
Yes, so this, I chose to give a dual view where the adversary. So generally, when you look at simulation theorems from the seminal papers, they're presented in a different way, where you're simulating a decision tree rather than simulating the adversary of the decision tree. But I felt that given that we're actively stifling, it makes more sense to present it as a person who's doing the stifling. It feels more natural in the setting, at least. It's possible that if someone gives a really nice presentation of the dual way, I might switch to that. But to me, for now, this is better. Yeah, so this is the proof that the number of queries needed, the number of queries that the parity querier needs to make is at least k times the decision tree complexity of R. So this is proving that the PDT number of queries needed is large. This isn't proving that the PDT size is large. And what we want for proof complexity is to prove that all PDTs need to have a large size. And that actually, it's really the same simulation. So if you want to do the same argument and show that the size is large, what we're going to use is the fact that we could answer these new parity queries arbitrarily. We're going to be a bit more clever here in order to prove that the PDT size has to be large. And what we're going to do a thought experiment where the querier is going to use the optimally sized parity decision tree. So we all know what the optimally sized parity decision tree is for this problem, and the querier is using it. And it's reached some point where the querier makes a query. This is at some point in the process of following the PDT, it makes a query. What we're going to do is we're going to answer it not arbitrarily, but we're going to answer it in such a way that the querier is going to go to the smaller side of the tree. So if T0 is smaller than T1, we're going to answer it so that the answer is 0. So it goes to that side. And what we gain by doing this is we're forcing the answer to be revealed in just log of PDT size queries. Because every time it's making a new query, we're answering it so that its size is halving. So that means that the querier is actually going to try to answer within log of PDT size queries. But nothing has changed from our earlier argument. It's still true that they need k times decision tree complexity of f many queries before they can answer. So that means that the log of PDT size has to be at least k times the decision tree complexity of f, which is exactly what we wanted. That's PDT size is at least 2 to the power k times decision tree complexity of f. It's a very neat trick that you get just by changing what you mean by arbitrarily. Size is the number of nodes. Since it's a tree, we don't make much of a distinction here. We just keep it as number of nodes in the tree. I mean, I guess everything I said would still work with number of leaves. You just go to the side with the smaller number of leaves. Right. So this brings me to, this ends the proof of the simulation theorem for the size version. And it brings me to an out-of-body experience that I once had around like a little less than a year ago at the Banff workshop for communication complexity. So this result was being presented, and I had this experience as if I was sitting in the audience and doing this presentation. And it was a bit unsettling until I got a ping from one of my co-authors. Dude, this sounds exactly like the sort of stuff we were doing. So it turns out that the same result was got by Paul Beam and Sajjan Karoth, and it was actually Sajjan Karoth who was giving the presentation, and I was actually in the audience. And so yeah, they had a result. They were looking at the indexing and inner product functions and various properties related to lifting and the structure of these functions. And one of the results that they had along these lines was that, yeah, if you use the indexing function as your composition, then you actually do get PDT size of R composed with indexing is at least 2 to the power of the decision tree complexity of R. So we then coordinated and got our papers out at around the same time online. Yeah, that was a fun experience. So, so that's all I wanted to say about the simulation theorem. But there are still a lot of open questions related to the simulation theorem. And one of them is to do with this inner product function itself. So the inner product function, it takes as input 2 t bits. And what it asks is, can you tell what the answer is of summation xi yi mod 2? So that's how many indices here have both of these bits set to 1. We want the answer to that modulo 2. And this is generally a very hard function. It requires, T communication complexity, so it requires T parity decision tree complexity and so on. But interestingly, if you look at how stifled it is, it's really not that stifled. It is one stifled. If you take any one bit here, I can set this other bit to 0, and therefore make that bit completely irrelevant and set the function output however I want. But it is not too stifled. If you take these 2 bits here, I can put whatever bits I want over here, but these 2 bits have enough power to flip the answer. So I can't set it to 0 or set it to 1. So this doesn't give us as strong a lower bound that we want. It does give us a composition with inner product. So we'll get that the parity decision tree complexity is at least the decision tree size of the relation, but we don't get T times the decision tree size, which is what we really want. Yeah. So in this case, what other parity pooper can we find that can actually prove this result? And this is, I feel like the more ways we can attack parity, the better it is for us in general. And so I think of this as, despite it being like a toy question, a pretty important problem. There are many other properties that we should be able to exploit. What are they? So this is the least important, but my most favorite of the open problems. We haven't seen it. Yeah, I mean.
So the low bound itself is open.
Sorry?
The low bound itself is open.
Yeah, the lower bound itself.
So if you make a parity query in one of those columns, red,
Yes.
set the pair to 0.
Right. So you make a query, and then you set. Oh, at that moment itself, you set the 0.
Yeah.
But so
the parity query, yeah, you should be safe, because the only bad thing would be if you ask both of them, but if you just got the parity of it, then you could do 1, 1 or 0, 0.
Yes. So you make a parity query. It's going to, we think of it as affecting 1 bit, and you don't wait for more parity queries to be made. You just set the other bit to 0 and continue the query.
Keep it so it starts.
And until, yes, so suppose you made T-1 queries, it sets everything here. You still have enough power to set the value to both 0 and 1.
No, but what if the parities sums? Oh, yeah, okay.
No, I think this works. It's a more involved process for the adversary, but it's still very straightforward rollout. Can you do something for your theoretic? In fact, it's a good learn on. Yeah, so I guess this would also work. I'm just a bit disappointed that we don't have a new property of parity that we're using here.
Do you get an issue with doing the size version of it? Because now if I'm setting all these other bits, then there may be queries that happen, or I don't get to go to the smaller side. I actually just forced to go to the bigger side.
Oh.
Yeah, we can actually, whenever this thing is being marked as red or as something that's being constrained, we can go to whichever side we want to, and then set the value of the other one to 0.
Sure. Oh, but whenever a query comes
No,
up.
but if those pair of bits are, say because if the parity just depends on those 2 pairs,
Yeah.
then if you set it to 0, then you're forced to go take the side of 1.
Oh, that's it.
So that'll get you the decision tree, but not
Yeah,
the
but
size.
not the size one.
The left size.
It is query like this too, and if it's 0, 0, it can be.
Sorry, could you explain again why it's not too stifled? I'm confused.
Why this is not too stifled? So suppose you're trying to stifle these two bits here. So by the definition of stifle, it means that I should be able to set the rest of these bits in such a way that the function value is already determined. And determined to 0 and determined to 1, depending on what I want. But the thing is, no matter how I set this, you can set this to say 0, 0, in which case, sorry, that's sense. So suppose you set this in a certain way, and you have summation xi yi for everything except the last coordinate. Suppose that is equal to b mod 2. If this is set to 1, 1, then the answer to inner product would be b plus 1. Mod 2. And if it's set to anything else, it would just be b mod 2.
But isn't it the other way around that like somehow that you want to fix those marked bits first and then you
Oh, no,
want
no.
to use the other bits to
We're treating
extend
them
to
as
0 or 1? Or
It's the other
no?
way around.
Fix the indices.
We're just marking them as affected bits because they're affected in a very complicated way. They depend on the summation of other things. We don't want to deal with that.
Oh, that's why I get it. Okay, then I see. It's a different definition. Okay, I see.
There's just to mention something, this might be random, but there's like an old paper, some old papers by me and maybe other people that look at like you take something that's hard for tree resolution and then you lift it to something, whatever, and then you look at it, you look at like the tree like a pregnant proof where you're allowed to query something from some class. So in your case, you're in parities.
So it's a different.
And what you require is that there's really strong correlation of lower bounds between the gadget function and the thing you're querying. So in other words, if the function that you're allowed to query can't really get to the value of the index gadget or whatever the gadget is.
So it doesn't help much in distinguishing.
Yeah, so we put lower bounds as long as you have this strong average test correlation. I don't know.
So it feels like a little bit.
It feels like maybe it does, it probably does as a special case, but I'm not sure. But maybe I'm bringing it up just because maybe it's a more general definition and stuff.
Yeah, it definitely doesn't play.
Also, just one. So, but when you're doing that, so some silently, you're. Whenever I get a parity query, I like pick one bit, and that's sort of the parity of the other guys. But and this choice is somehow being made for us adversarially. I mean, we're not trying to do it in a smart way. We're just picking the first guy, say, and it's like.
Even
Because in some sense, if you were doing a lower bound, then and in fact we are picking the bits we're sort of committing to as a function of the other bits. And I would try to avoid getting a column like this.
Sure.
But you might not be able to. Somebody might have queried that column. That might have been buried.
You can just remember the variable you're going to keep around and then all the other variables are like totally free. That's what I think it is.
Yeah.
So one thing about this stifle, just because we had this whole discussion, is like you said, inner product isn't too stifled because it was 2 bits.
Yep.
But it is too stifled if I add in a new constraint, which is instead of letting these 2 things be set however I want, I'm going to add some, I have a parity constraint determining the top one, and I have a parity constraint determining the bottom one. I'll throw in a third parity constraint that says the parity of the 2 of them is 1. For example, at which point these necessarily give 0 when you take the product. And now you can continue on such. So somehow, even though it's not too stifled, it's very close to being, T minus 1 stifled as far as parity constraints are concerned.
So you think of this as being some kind of promised inner product where some constraints are already made on pairs that are stifled? No, I see that there are ways to go ahead and make it to stifled in some sense. I just don't see where this extra constraint comes in from.
I'm saying, you could imagine, I'm simulating a parity decision tree. So as long as you haven't forced those 2 bits to be, I can just say, all right, you've queried these 2 bits, I'll give you a 3rd constraint for free. As a present.
But it has to be like compatible with the constraints that they're making.
Yes, but. Okay, but if they're both fixed to be 1, for example, then, okay,
Then it would be.
then I'm fine. If you fix those 2 bits, then, you just get a slightly smaller product.
Right. So yeah, if it's more query-like, then it's more immediate cycle. But when they're parity, it's hard to say what they're doing behind the scenes.
Could you do something like you say, I only query, so I think there's a combinatorial that says, if you're in any subspace that's sufficiently high dimension, the inner product is not yet fixed. So could we wait until a parity constraint is about to lower the dimension of a particular block below that threshold, and then fix the bit in that block that to be however we want.
I think the proof I'm talking about is, I think that's more kind
That's what you do? Yeah.
Okay.
But a parity is simultaneously looking at various blocks, right?
Yeah, but you could just say, as long as there does not exist a block where if I restrict it to that block, I'm below the threshold, then it doesn't matter. All the inner products are kind of free. It's only when a block is about to become critical that I say, forget about now I'll look at the constraints in that block that affect that block. Okay. And I'm just gonna simulate, remove that set of T constraints by just fixing the value in that one block.
So this might work if you're treating the blocks as like independent blocks.
But okay.
But there could be parity constraints that have made correlations between blocks, which.
Well, but you're saying we're just gonna. Okay.
That's true. That's true.
The rest of it's fine.
Yeah, we're kind of making it independent.
I'm not sure if you're done or not.
If people want to look at it,
So I don't
okay, so
okay, good. Yeah.
these are the other. Can we prove mod PDT lower bounds? There's a problem with the way we fix variables. We can just inadvertently make some of our variables not in 0,1. I don't have time to go into going over time. And of course, the main of the problem is, can we prove lower bounds for parity DAGs? This has actually already been proven. PHP requires large mod PDTs by Parton Zamarat. And it uses like the first trick of parity decision trees that we looked at, where if you've made a few constraints, there's always another solution. Yeah.
Any other really quick questions? I think there's a reception soon.
Now?
So the width of a line is just the number of parties that.
My translation.
Much as well.
You want to lift?
Proof combined.
So,
No, I was asking just for the
yeah, so, yeah, I mean, if you want to think about it, I mean, I guess it's just the dimension of the affine subspace. Like if you think about it as each line as a subspace, it's just dimension of the affine subspaces involved in the, sorry, codimension of the affine subspaces
involved in the proof.
I will ask you.
Great, thank you.